Students, we were doing calibration curves. Now let's see some examples of calibration curves. Examples of calibration curves. Let's discuss some examples of calibration curves. Now, the first example that we have to see is a mercury in glass thermometer. And a calibration curve is basically a graph between the actual and the apparent quantity of an instrument. For a mercury in glass thermometer, the actual quantity is temperature, and the apparent quantity is what you observe is called the apparent quantity. What you want to read is called the actual quantity. The apparent quantity is the length of the mercury column. So the actual quantity is the temperature and the apparent quantity is the length of the mercury column. Now, different designs of thermometers could be discussed. First of all, let's suppose we have this design with uniform divisions. It has uniform sensitivity. Size of divisions is uniform throughout. So 0, 1, 2, 3, 4, 5, 6, 7, 8. Now, this is a thermometer which has uniform divisions. Or you can say that this thermometer has a uniform sensitivity. So, length moved by the mercury column or height gained by the mercury column for every 1 degree Celsius rise in temperature is same at any point. So that's why this thermometer has a uniform sensitivity. Now, if we plot a graph between the length of mercury column along with temperature in degree Celsius, then this graph would be a straight line through the origin. The reason for a straight line is uniform sensitivity. So this thermometer has a uniform sensitivity throughout. So that's why the graph is a straight line. And one thing, you must remember that if the divisions are getting bigger, then the graph will bend towards the apparent axis. And if the divisions are getting smaller, then the graph will bend towards the actual axis or away from the apparent axis. Let's suppose we see another example in which we have this thermometer, in which initially the divisions are smaller then they are getting bigger and bigger. So at high temperature, it is more sensitive, or sensitivity is increasing with the increase of temperature. Divisions are getting bigger. So in this thermometer, divisions are getting bigger with the increase of temperature. Divisions are getting bigger with the increase of temperature. We can say that it is more sensitive. It is relatively more sensitive at high temperature. So this type of thermometers are designed to be used in a region of high temperature. An instrument must be more sensitive in the region where it is supposed to be used. Now, if we draw a calibration curve for this thermometer, then you must understand that the graph will bend towards, you see, this is length in centimeter, and this is temperature in degree Celsius. Now, one thing that you have to understand is that first differentiate the apparent and the actual quantity. As you see here, this is the apparent quantity, and this is the actual quantity. Now, when the divisions are getting bigger, the graph will bend towards the apparent axis. Here, as you see, this graph will bend towards the axis of length, because that is the apparent axis. So when the divisions are getting bigger, the graph must bend towards the apparent axis. One more thing, in some cases, the axis of the graphs will be changed. Just for example, you may have temperature on the y-axis and length on the x-axis, but it will not matter, as the calibration curve will remain same. Since the divisions are getting bigger, so it will bend towards the length axis or the apparent axis. Now, the principle is that whenever the divisions are getting bigger, the graph or the calibration curve will bend towards the apparent axis. And here the apparent quantity is length, so the graph will bend towards the length axis. Now you see, another example could be when you get a situation in which the divisions start to get smaller. Then you get a situation where the divisions start to get smaller. 0, 1, 2, 3, 4, 5, and so on. Now, in this thermometer, let's suppose this is mercury and glass thermometer. In this thermometer, the thermometer is becoming less sensitive at higher temperature. So we can say that with the increase of temperature, the sensitivity is decreasing. The divisions are getting smaller. So this one is less sensitive at high temperature. Such thermometers are good to be used for low temperature applications, since it is more sensitive at low temperature. Now, if we plot a calibration curve for this thermometer, then you must know that it is length in centimeter against temperature in degrees Celsius. Now you see the divisions are getting smaller. The graph will bend away from the apparent axis. So whenever divisions get smaller, the graph will bend away from the apparent axis. On the y-axis, we have apparent quantity, and on the x-axis, we have the actual quantity. And in this example, since the divisions are getting smaller, it will bend away from the apparent axis. Sometimes the axes are changed. It could be the temperature is on y-axis and length is on x-axis. It will not matter, as still the principle is same. Since the divisions are getting smaller and the graph has to bend towards, away from the apparent axis. So this is the graph. So the graph may bend towards the apparent axis or away from the apparent axis. If the divisions are getting bigger, it will bend towards the apparent axis. If the divisions are getting smaller, it will bend away from the apparent axis. Now the summary of all this is that if you get a situation where the divisions are uniform, then the graph would be let's suppose this is the apparent. A calibration curve is graph between apparent quantity and actual quantity. Here you see the divisions are uniform. When the divisions are uniform, the graph is a straight line through the origin. So this is a calibration curve with uniform sensitivity. This is a calibration curve with a uniform sensitivity. Second example is when the sensitivity is increasing with the increase of value. So this device is becoming more sensitive towards high temperature, towards high value. So sensitivity is increasing. For this device, sensitivity is increasing. For this device, the calibration curve would be, this is apparent quantity, this is actual quantity, and as you see the divisions are getting bigger, the graph will bend towards the apparent axis. Simple as that. And if the axes are changed, if apparent is on x-axis and actual is on y-axis, still the graph will bend towards the apparent axis. So the second example is for the device for which the sensitivity is increasing. The third example that we see is for a device in which the divisions are getting smaller and the sensitivity is decreasing. Let's suppose this is 0, this is 5, 10, 15, and so on. Now in this device or instrument, you see that the divisions are getting smaller. So we can say that the sensitivity is decreasing. So for this device, the sensitivity is decreasing. And the graph would be, this is apparent, this is actual. This graph will bend away from the apparent axis as the sensitivity is decreasing. And if the axes are changed, if apparent is on x-axis and actual is on y-axis, still the graph would be same away from the apparent axis. So this third example is when the sensitivity is decreasing. Uniform sensitivity straight line graph. Sensitivity increasing towards the apparent axis. Sensitivity decreasing away from the apparent axis. Simple as that. Now let's see examples of some voltmeters and their calibration curves. You must know that for an analog voltmeter, the actual quantity is the voltage and the apparent quantity is the angle of deflection, because they have the pointers. Now let's suppose we have some analog voltmeters. Now let's suppose we have some analog voltmeters, and an analog voltmeter has apparent quantity for any analog meter. The apparent quantity is angle of deflection moved by the pointer. For any analog instrument, the apparent quantity is angle of deflection moved by the pointer. And the actual quantity for a voltmeter is obviously the voltage. Actual quantity for a voltmeter is the voltage. And a graph between voltage and angle of deflection will be called calibration curve of an analog voltmeter. Let's see some examples of voltmeters and their calibration curves. Example number 1, you have a voltmeter which has uniform divisions 0, 5, 10, 15, 20, 25, and this is the pointer when it is off, and this is the voltage. Now you have to plot a graph of voltage on the y-axis and angle of deflection on the x-axis. So voltage on the y-axis and angle of deflection on the x-axis. This is the calibration curve for the first meter. Second example is when the sensitivity is increasing. The divisions are getting bigger. Now you see the divisions are 0, 5, 10, 15, 20. However, the size of divisions is increasing. This is the pointer and this is another analog voltmeter. you have to plot a graph of voltage against voltage is the actual quantity on the y-axis against angle of deflection on the x-axis. So you have to plot a graph of voltage on the y-axis against angle of deflection on the x-axis. The third meter we have to observe is the one in which the sensitivity is decreasing. So 0, 5, 10, 15, 20 and so on. This meter starts with, this is the pointer when it is off. For this meter, what would be the graph of voltage against angle of deflection? So basically, you have to plot a graph of voltage against the angle of deflection for all the three meters. The first meter is the one with uniform sensitivity. The second meter is the one in which sensitivity is increasing. The third meter is the one in which the sensitivity is decreasing. The second meter is suitable to be used at for high temperature applications. The third meter is more suitable for low temperature applications. When it has a uniform sensitivity, it's like this. When the sensitivity is increasing, it will go towards the apparent axis, that is the angle. So the reflection or angle or the division is getting bigger. The graph will bend towards the division axis, angle axis. In the third example, as you see, the division is getting smaller. So the graph will bend away from the division axis or the angle axis. So these are the three calibration curves for the given 3 meters. We are done with that. The same concept will apply to all the other analog meters. It could be analog speedometer of a vehicle, in which the speed of the vehicle will be the actual quantity and the angle of deflection will be the apparent quantity. Same is for an analog ammeter. If you have an analog ammeter, the current will be the actual quantity and the angle of deflection will be the apparent quantity. Same is for an analog fuel meter of a vehicle. In an analog fuel meter of a vehicle, the fuel volume of the fuel is the actual quantity and the angle of deflection will be the apparent quantity. So we can use any of the analog meters as example. And for all the analog meters, the angle of deflection will be the apparent quantity. Now the next topic that we have to cover is zero errors. How to represent zero errors in calibration curves. Zero errors in calibration curves. Now you have to understand that there are two types of zero errors. One of them is a positive zero error and the other one is the negative zero error. First, let's understand the concept of positive zero error. A zero error is called positive zero error when, first of all, the instrument will not read 0 but it will read a positive value when off. So in case of positive zero error, the instrument will not read zero, but a positive value when it is made off. And the second thing is all the readings, taken by this instrument will be greater, they will be bigger than the actual value by a fixed amount. So in case of positive zero error, you will get a reading that is always greater than, your reading will always be greater than the actual value. And one thing, reading minus actual value, here you will get a positive constant, and the positive constant that you will achieve will be the positive zero error. So this is all about a positive zero error. A positive zero error is there when first of all the instrument will not zero, but it will read a positive value when it is made off. It will be on the right hand side of zero. And the other thing is the reading will always be greater than the actual value by a fixed amount. And that fixed amount is called the positive zero error. Then we have the other type of zero error that is called negative. The other type of zero error is called a negative zero error. The second type of zero error is called a negative zero error. In case of a negative zero error, the instrument will not read zero, but a negative value when made off. So the instrument will not read zero, but it will read a negative value when made off. And the other thing is the reading will always be, the reading taken from this instrument, the reading will always be smaller than the actual value by a fixed amount. So here reading will be smaller than the actual value, and if you subtract the actual value from the reading minus actual value will give a negative constant. It will give a negative value that would be fixed, that would be constant, and this negative constant is called negative zero error. Now we have to see that how will we represent this positive zero error and this negative zero error on a calibration curve. This topic and CRO will be covered in the next class, inshallah, and then we'll start kinematics. Take care, students. Khuda Hafiz.